So instrumentation amplifier. So what is meant by instrumentation amplifier? So this amplifier is supposed to be used in most of the industries. Since it is used in industries, so that is why it is called as instrumentation amplifier. Okay, in industries, there are certain things where we have to measure some physical quantities. The physical quantity is like nothing but a temperature, pressure, humidity, etc. Okay, those are the things which are the parameters of an industry, and these parameters are supposed to be measured by using a device called transducer. By using a device called transducer. So that means a transducer is the one which converts one form of energy into other form. One form of energy into the other form. For example, the transducer otherwise called as a sensor as well. Transducer otherwise called as a sensor. So which converts one form of energy into the electrical signal. So that means, for example, take thermocouple. A thermocouple is a transducer in which it converts heat energy into the electrical energy or electrical signal. Similarly, microphone. So what we are nowadays using, that is mic. So mic is nothing but the sound energy is converted into the electrical energy. Similarly, strain gauge. Strain gauge is nothing but a type of a device in which the pressure or mechanical forces are converted into the electrical energy. So you can see strain gauges in most of the weight devices. Weight, where you can find five electronic weights. So there you can see the strain gauges. So that means, so each and every industry, okay, is supposed to use certain parameters. So those parameters has to be measured very carefully and precisely. Those parameters has to be measured carefully and precisely. So in order to measure that one, we are using a device called a transducer. A transducer is the one which converts one form of energy into the another form. Okay, that means that, for example, take a thermocouple, it converts heat energy into electrical energy. Microphone, sound to electrical. Strain gauge, pressure, force like mechanical energy into the electrical energy. So that means that the physical quantity, the physical quantity is proportional to that of the electric signal. The physical quantity is proportional to that of the electric signal. Okay, and the signal that is coming from the transducer can be used for further controlling the device, or it may use it for display, or it may use for recording purposes. Okay, but the thing is that the output of a transducer is very low signal. The output of a transducer is very low signals, which will be in the order of millivolts or even microvolts, which will be in the order of some millivolts. And this millivolts signal cannot drive the next stage of the system, cannot drive the next stage of the system. So therefore, and also, since it is very low signal, since it is very low signal, and this signal is subjected to noise very quickly. This signal is very subjected to noise very quickly. And at the same time, the transducers which are talking about is not very near to that of the control room. So it is mounted on the equipment, so which is far away from the control room. For example, take a thermal power plant. Thermal power plant. So in thermal power plant, we have boilers. We have boilers. So these boilers are at most of half a kilometer from the control room. Half a kilometer from the control room. So these boilers, on the boilers, we are supposed to be mounted the temperature sensors and pressure sensors. Okay, and the output of temperature sensor and pressure sensor, which is from the transducer, are very low signals, and at the same time these signals has to be carried towards the control room. So in order to carry these signals, we are using certain cables like a long connecting wires or cables. So whenever we are transferring these small signals through these connecting wires, these signals are subjected to some noise and this atmospheric interference. Okay, so when this subjected to some noise, what will happen? The performance, the quality of the signal will reduces. The quality of signal will reduce. That means that the signal is attached by the noise. The signal is attached by the noise. So therefore, Therefore, we have to reject these noises. We have to reject these noises, and at the same time, the small signal has to be amplified. At the same time, the small signal has to be amplified. A ordinary difference amplifier cannot do this thing. A ordinary differential amplifier cannot do this thing, and therefore a special type of amplifier, which is referred to nothing but the instrumentation amplifier, is used in this case. So okay, uh, so in order to reject this noise, and at the same time we have to amplify this signal. So that is, a ordinary differential amplifier cannot serve this purpose, and therefore we use a special type of amplifier, so which can amplify the low level signal and which has high CMRR. That means that it has to reject the common mode signal. It has to reject the common mode signal such that the performance of the amplifier is increased, and at the same time it should have high input impedance and it has low power consumption. Okay, and this special type of amplifier is referred to nothing but the instrumentation amplifier. This type of amplifier is nothing but the instrumentation amplifier. Okay, so this instrumentation amplifier is also called as a data amplifier. This instrumentation amplifier is also called as data amplifier, and it is basically a differential amplifier. And it is basically a differential amplifier. So that is why we go for instrumentation amplifier. Again, we'll come into the same what is meant by instrumentation amplifier. So in take any industry. So industries will have certain parameters in order to measure precisely. Okay, so these parameters, so which you use to measure precisely, are carried over by a device called transducer. So that means that a transducer is one which converts one form of energy into the other form. Okay, that is by, for example, take a temperature. So for temperature, we use a temperature sensor or thermocouple. So that means that a thermocouple is the one which converts the heat energy into the electrical energy. Similarly, mic, sound to electrical energy, strain gauge, pressure or force like mechanical energy into the electrical energy. So therefore, the output of a transducer is nothing but a electrical energy which is proportional to that of the physical quantity. Okay, and the one bad thing in this transducer is nothing but this transducer will have the output of a transducer is nothing but a very low level signals, and these signals cannot serve the need for the next stage of the system. Okay, so therefore, and at the same time, these transducer are not very near to that of the control room, and these transducers are supposed to be mounted on the equipment which is far away from the control location. Okay, so that means that the transducer that are converting the physical quantity into electrical signal has to be travel at far to that of the control room. Okay, so in order to travel these signals from from the transducer to the control room, we are supposed to use some connecting wires and cables. So since these signals are very low level signals, when it is traveling into the cables, it is subject to some noise and due to the atmospheric interference. So because of that one, what will happen? The quality of the signal will reduces. The quality of the signal will reduces because of the addition of the noise. So this type of signal cannot be amplified. So when this type of signal has been amplified directly, what will happen? The noise will be overcome. The noise amplification will be overcome by the actual signal. So we have to reject this noise, and at the same time we have to amplify the signal also. So the normal differential amplifier cannot do this serve this purpose, and therefore we need a special type of amplifier, so which rejects the unwanted signal, which is nothing but the which has a high CMRR, and at the same time it has to amplify the low level signal. It has to amplify the low level signal, and it has a high input impedance, and it has some low power consumption. Okay, and this type of amplifier is nothing but the instrumentation amplifier. Okay, and this instrumentation amplifier is also called as data amplifier, and it is basically a differential amplifier, and it is basically a differential amplifier. So let us see the expression for this one. The expression of the instrumentation amplifier will be in the form of A is equal to V naught by V2 minus V1, where V naught is nothing but the output of the amplifier and V2 minus V1 is the differential input that is to be amplified. The expression for voltage gain of instrumentation amplifier will be in the form of a differential amplifier. So which is nothing but A is equal to V naught by V2 minus V1, where V naught is the output of the amplifier and V2 minus V1 is nothing but the differential input which is to be amplified. So therefore, the instrumentation will amplifier will have certain features, or otherwise the requirements of the good instrumentation amplifier. So the it also referred to as features or requirements of the instrumentation amplifier. The features of requirements of instrumentation amplifier are nothing but high gain accuracy. High gain accuracy. The gain of the instrumentation amplifier is very gain and it is accurate and it has high CMRR. So we know that what is CMRR? CMRR stands for common mode rejection ratio. So lesser the value of common mode gain, better the performance of the system. That is higher the CMRR. So higher the CMRR, better is the performance of the amplifier. So it has high CMRR. It has high input impedance. Since it is basically a difference amplifier, we know that the difference amplifier will have high input impedance. So therefore, we can connect n number of inputs to the same thing. So that has high input impedance and low output impedance. So the low output impedance is nothing but since instrument amplifier consists of op amp, we know that the output stage of op amp will have a push-pull amplifier. So where we have low output impedance. So that means that the output of the instrument amplifier can be connected to n number of circuits as well. Okay, and its gain is stability with low temperature coefficient. That is, whenever there is change in temperature, the gain will have the same value. There will be no change in the gain. So that is nothing but high gain stability with low temperature coefficient and low DC offset. Low DC offset. So what is meant by offset? What is meant by offset? So offset implies nothing but whenever there is no input, the output should also be zero. The output should also be zero. But in practical cases, so even though we are not giving any input, okay, the output will show some certain value, which is very, very less value. The output will show certain less value. So that means that at the output side, we have some value without giving any input. Okay. And that value has to be compromised. That value has to be made zero. Okay. So in order to give the input. So for making the output zero, we are applying a additional DC input voltage in order to make the output zero. Okay, that is referred to nothing but the offset voltage. So that is referred to nothing but offset. So in case of instrumentation amplifier, the offset voltage is very, very less. So that is why referred to nothing but low DC offset. Okay, so these are the requirements of good instrumentation amplifier or features of the instrumentation amplifier. So the instrumentation amplifier will have high gain accuracy, high CMRR, high input impedance. Why? Because it is a basic differential amplifier. Low output impedance. This implies nothing but it is nothing but a op amp. So output of the op amp will have push-pull amplifier where we can have the low output impedance. So therefore, you can connect to n number of circuits and the same manner the input of the instrumentation amplifier can be given n number of inputs as well, and therefore there will be no loading on the driver side. And next it has high gain stability even though there is change in temperature, so the gain is stable. Okay, and low DC offset imply nothing but offset voltage is nothing but when there is no input there should not be any output, but in some practical cases there will be a small output that is present at the output side. Okay, so in order to nullify that output, we are giving an external input voltage such that to make the output zero. So that is referred to nothing but offset. So in case of instrumentation amplifier, the offset voltage that we are giving is very, very less, which will be in the order of some millivolts or microvolts. Okay, so that is referred to nothing but the features of instrumentation amplifier. And coming to the actual instrumentation amplifier. So generally the commonly used instrumentation amplifier is nothing but 3 op-amp instrumentation amplifier. 3 op-amp instrumentation amplifier. Here we have 3 op-amps. So A1, A2 and A3 are nothing but the 3 operation amplifiers. So in which A1 and A2 are nothing but the non-inverting amplifiers. A1 and A2 are nothing but the non-inverting amplifier. See, the input is given to the plus terminal, and here the input is also given to the plus terminal. So therefore, at the input side, at the input stage, we are using two non-inverting amplifiers. We are using two non-inverting amplifiers. And coming to the output stage, so which is nothing but a differential amplifier. See, so this is the minus, and this is plus, and the output of A1. So let us take output of A1 is V01 is given to the one input terminal of the A3 amplifier, and the output of V2, that is take it as V02, is given to the other terminal of the op amp. So therefore, the second stage, that is the also referred to as output stage, is referred to nothing but a basic differential amplifier. Is basic a difference amplifier or differential amplifier. Okay, or I can take it as a subtractor as well. So whatever maybe all the things are equal. Okay, so here the thing is nothing but, so the basic amplifier that we are using nothing but 3 op amp instrumentation amplifier, in which at the input side we have two non-inverting amplifiers. So where we can give inputs. So V1 and V2 are nothing but the two inputs that are given to the two non-inverting amplifiers, and V1 and V2 are nothing but the differential voltage that is coming from the transducer. Two differential voltage that is coming from the transducers. Okay, and the second stage or after the output stage, it consists of a difference amplifier where the outputs of the two non-inverting amplifiers is given to the a difference amplifier, and finally the output will be the difference of the two input signals. Okay, this is how a instrumentation amplifier looks like. So it has three operation amplifiers. A1, A2 are nothing but non-inverting, and A3 nothing but a differential amplifier. A3 nothing but a differential amplifier. And coming to the theory, the theory is what we have discussed before. It is commonly used instrumentation amplifier. It has high input impedance, and it is used for measurement of signal that is coming from the transducer. In the circuit, we have two non-inverting amplifiers, and which is added to that of a differential amplifier inputs. Here, op-amp A1 and A2 are nothing but the non-inverting amplifiers forming the input stage, and op-amp A3 nothing but the normal difference amplifiers forming the output stage. So therefore, the output of the difference amplifier, instrumentation amplifier, will be given as V0 is equal to R2 by R1 into 1 plus 2RF by RG into V2 minus V1 into V2 minus V1. So this constitutes nothing but the instrumentation amplifier. And coming to the analysis. So coming to the analysis of the circuit. So let us consider the output stage first. Let us consider the output stage first. See here, the output stage is nothing but a difference amplifier. The output stage is nothing but a difference amplifier, in which the inputs of the difference amplifier is coming from the two non-inverting amplifiers. So let us consider the output of A1. So this is the output of A1. So it is nothing but V01. Similarly, the output of A2 is nothing but V02. Output of A2 nothing but V02. So that is what I specified here. The output of A1 is V01, the output of A2 is V02, and it is given to the two terminals of the difference amplifier. Okay, and therefore, from the analysis of differential amplifier, what we have discussed before, that the analysis of differential amplifier, the output V0 is equal to R2 by R1 into V02 minus V01. Output V0 is equal to R2 by R1 into V02 minus V01. Now, what the thing we have to do is nothing but we have to find the V02 minus V01 in terms of V1 and V2. In terms of V1 and V2. So V1 and V2 are the actual inputs actually. Okay, but whereas V02 and V01 is the inputs for the difference amplifier, which is nothing but the outputs of the two non-inverting amplifiers. So for the two non-inverting amplifiers, we are giving the inputs as V1 and V2, and therefore the output should be in terms of V1 and V2. The output should be in terms of V1 and V2. So similarly, so that is how the input stage. So this is the input stage where we have given V1 and V2 the inputs, and V01 and V02 is the outputs of the A1 and A2. Okay, and RF1 and RF2 are nothing but the feedback resistances. Feedback resistances. So which similarly looks like this. So this is the signal. So plus, and this is the things. So which can be look like this. So this is nothing but R, which is nothing but the feedback signal, which is given to the non-inverting term, which is given to the inverting terminal. Okay, which is similar to this one. So these two are similar. This is and this is similar. Only thing is we have make the resistance this side. Okay, and here the thing is nothing but here we are using a RG resistance. So which is nothing but the gain resistance, which is nothing but the gain resistances, and which is nothing but a potentiometer, which is nothing but a potentiometer. So the advantage of this instrumentation amplifier is nothing but the advantages of instrumentation amplifier is nothing but if you simply change the gain RG, the entire gain of the amplifier will changes. If you simply change the resistance RG value, the entire gain of the instrumentation amplifier will changes. So therefore, it has the advantage that if you place this resistance at the output side of the op amp, if you change this resistance implement, automatically the gain will change. So that is the advantage of this one. So the EG adjustment of gain can be possible here. EG adjustment of gain can be possible here. And so here, let us take the A1, A1 non-inverting amplifier here. A is at which potential? V1 potential. So since A is in the node at the non-inverting terminal, and similarly node B is also should be at the same potential by the concept of virtual ground. So if B is at same potential, automatically G is also at V1. G is also at same potential. So which is equal to V1. Similarly on the bottom side also. Similarly in the bottom side also, D is at V2 potential, and therefore by the concept of virtual ground, C is also at V2 potential only. Since K is connected to the point H, and therefore again the H is also at V2 potential. H is also at V2 potential. And now here no current is flowing through the op amp. Why? Because it has high input impedance. So therefore entire current will flow through the points in this direction. Entire current will flow through the three resistance RF1, RG and RF2. So completely. So that means that from E to F the current will flows. From E to F the current will flows. And now let us see applying Ohm's law from E to F. Applying Ohm's law from E to F. So I is equal to V01 minus V02. So this is V01 minus V02 by the total resistance RF1, RG and RF2. Now let us consider RF1 and RF2 is equal to RF, and therefore we have V01 minus V02 by 2RF plus RG. It is 2RF plus RG, and therefore now consider the nodes G and H. Consider the nodes G and H. So when consider the node G and H, the same current is flowing here. Therefore, I is equal to Vg minus Vh by Rg. Vg minus Vh by Rg. So since G is nothing but V1 and H is nothing but V2, and therefore I is equal to V1 minus V2 by Rg. Since both the currents are equal, so equating 3 and 4 equations. Equating 3 and 4. So when equating 3 and 4, we have V01 minus V02 by 2RF plus RG. 2RF, this is not R1, F1, this is RG, RF, which is equal to V1 and U2 by RG. So, but we have to get in terms of V02 minus V01, and therefore interchange the things. So V02 minus V01 and V2 minus V1. So interchange these things. This is interchange, this is minus, and interchange these things. When interchanging this, what will happen? So V02 minus V01 by RF, this is RF only, RF plus Rg, that is V2 minus V1 by Rg. So therefore V02 minus V01. V02 minus V01 is equal to V2 minus V1 into 2RF plus RG by RG. Now substituting that V02 minus V01 in equation 1. So what is equation 1? So this is the equation 1. So substitute the value of V02 minus V01. So when we substitute the value of V02 minus V01 and simplifying, we'll get it as V0 is equal to R2 by RF into 1 plus 2RF by RG into V2 minus V1. So all these cases is RF only. All these cases are RF only. So this is the overall gain of the op amp. This is the overall gain of the op amp. See here, if you simply change the value of RG, if you simply change the value of RG, so automatically what will happens? The gain will changes, the output will changes. The output will changes. Here the gain is nothing but V0 by V2 minus V1 is equal to R2 by R1 into 1 plus 2RF by RG. So this is the instrumentation amplifier. Okay, so understood? So the instrumentation amplifier is nothing but a special type of amplifier in which it is nothing but a special type of amplifier in which it has high input impedance, it has high input impedance, low output impedance, high CMRR, and it has low DC offset, okay, and many more features So this constitutes nothing but the differential amplifier. This constitutes nothing but the differential amplifier. So have you understood? So this is about the instrumentation amplifier. So it is basically a 3 op amp. It consists of 3 op amps. So at the input stage we have, at input side we have two non-inverting amplifiers, and output side we have the difference amplifier. The output of the two non-inverting amplifiers given to the inputs for the differential amplifier. Okay, so A1, A2 are the non-inverting amplifier, and A3 is nothing but the difference amplifier. Okay, so since the output is a difference amplifier, and therefore V0 can be taken as R2 by R1 into V02 minus V01. And coming to the analysis of the input stage, so since these are two non-inverting amplifiers, and solving the equations, and finally we'll get as the output V0 is equal to R2 by R1 into 1 plus 2RF by RG into V2 minus V1. So if V2 minus V1 goes to the left side implying that is nothing but gain of the amplifier. Here the simply if you change RG, automatically what will happens? The gain will changes. If you change RG implying nothing but the gain will changes. Okay.